So the chapter that we're starting today, which I called in the syllabus Infinity, is about counting things. So to talk about that, what does it mean? What does it mean to count something? Whenever we're trying to measure an object in real life, what that usually means is that we are comparing it to some other object whose size we already know, either because we measured it first or because we agreed that it has a fixed size, like a ruler or a meter or whatever other measurement tool they used in antiquity, which have been many efforts to standardize this, right? So to count means to measure by comparing with some object whose size is known. Now here's a very simple example that I want to show you to highlight the point I'm trying to make. So this might be too simple of an example, but it's better to start with something too simple than too hard, and then we can build from this intuition. So this is a combination lock. So for example, how many combinations can you form? And I already see some answers. 10 to the fourth power. That is correct. And the way that you figure out that the correct answer is 10 to the fourth power is because each dial, each number wheel can have exactly 10 digits. So the easiest thing that we can do to figure out what the answer is to this question is if we just count them one by one, then the first combination, depending on, let's say we pick the simplest order that we can start, would be this one, right? And then if we start turning the last, or let's say the first dial, this becomes a number one. And we can continue doing this until we reach the last number, which is 9,999. So this gives a total of 10 to the 4, right? Now this is easy enough because the object that we are counting, namely the combinations, are easily set in correspondence with numbers, the first 10,000 numbers. They are already spelled out for us. But clearly we can generalize this. If the dials didn't have numbers, but letters on them, say 1 out of 5 possible letters, then we could easily see that, let's say, a lock with letters instead, let's say A, B, C, D, E. How many combinations could you find in this case? Well, this would have 5 letters, and there's 4 positions, combinations. By the way, combination is probably not the best choice of words I should use. People call them combinations because this is called a combination lock, but we're not really counting the thing that I will later call combinations. So I didn't say this, but as part of the logistics of the course, I sent out this poll before the break, and in it was voted that the last chapter should be about combinatorics, which is why I'm trying to motivate this chapter, which is not combinatorics yet, but it is related to it. I want this chapter to be motivated by that, right? And when we see combinatorics, we will call a different object combinations, but that probably doesn't matter right now. Okay, so maybe I could actually mention this is the chapter 4, right? Infinity. Okay, so I haven't said anything too interesting right now, but if you notice, I've already generalized this idea to something that doesn't have numbers anymore. It's not spelling out which should be the first. I mean, of course, intuitively, The most natural thing to pick would be four A's in a row as the first combination, and then AAAB, and then AAAC, and so on, right? But this is no longer that obvious as if I'm using letters. So in general, how many what could we call them? K tuples of a set of n elements can you form? A K tuple is, of course, something of the form A1, A2, AK, where AI is in some fixed set A of size n, and I already have the answer. K to the n. K to the n. Right? So this generalizes this idea. But we could go even further. Another way to think about this. Let's generalize this even further. Imagine that we are picking 1, 2, all the way to k. And instead of thinking this as tuples, we can think of these as functions, can we not? 1 through k tells you what coordinate or what digit we represent here, and a is the set from which we're picking the numbers or the letters or whatever object will be written on the dials, right? Is functions. So how many functions are there? And the answer should be the same, right? It's actually okay. Shouldn't it be n to the k? Give me a second. How did I write this? Okay, this should be n to the k, should it not? So in the example above, each tuple is a 4 tuple because it has a first coordinate, a second, third, and a fourth one. And each element of the 4 tuple can be chosen out of 10 possible digits, right? So it's the size of A to the size of how many positions you have. So it's n to the k, right? Is everyone in agreement with that? Does it make sense? Please just stop me if something is unclear. So this is something that we will expand upon in the last chapter when we talk about combinatorics, because right now I only told you how many functions can we find that have a domain of size k, for example, the index of the coordinates, and the output or the codomain is some fixed set, right? I answered this question by telling you it's n to the k. And hopefully this intuitive explanation makes sense. If you want a more formal treatment of this, then the next tutorial next week will cover this in detail. We will actually prove that there are n to the k functions from any set of size k to any set of size n. Maybe I should write this down. So this is formalized. This idea is formalized in the next tutorial. Right, so please make sure you attend. The tutorials are supposed to complement the lectures, right? So I'm skipping on some technicalities, but for this, for the purposes of what I'm doing now, I want the intuitive, I'm giving more value or more weight to the intuitive explanation, right? So any questions so far? Does it make sense how this idea with the combination lock, which was very simple, how this connects to functions from arbitrary sets from one side to the other. Now, combinatorics, of course, treats with this in a lot more detail because we will be asking not just about functions in general, but special functions like injective functions, how many surjective functions, how many functions that satisfy this and that, that they are not allowed to repeat. You're not allowed to have consecutive numbers of the same type. We can change the question so that the answer becomes much more difficult to find. But this is the very first example of counting that I want to introduce. Okay, so this answers the question, why do we need counting? What do we need counting for? Now, there's something that I want you to remember, and this is the first topic, the first official topic of the chapter of infinity is cardinals. We're not going to define what a cardinal is, but I do want to talk about, still in this intuitive spirit, about what we're doing, right? So we've already seen cardinals before. Recall how we constructed the naturals. Now, we didn't do this formally. Instead of informally, maybe I should say naively constructed the naturals. So we did this in one of the earlier chapters, and the idea was as follows. So we defined a relation. Now I'm going to put this in quotes, and I'm going to explain in a second why. On sets. Now I've defined this before, but let me just remind you what this is. Two sets are said to have the same cardinality or the same size or equipotent or equinumerous. All of these are synonyms, right? If there is bijection between them, right? Bijection, of course, can be in any direction, either from A to B or in reverse, because you can always take the inverse and then you have a bijection that goes the other way, right? So this relation behaves like an equivalence relation, and we proved that. We proved that it behaved like an equivalence relation. Now, if you go to Wikipedia and you look up equinumerosity, you will see this relation defined, I think the same way that I defined it right now, and you will see this weird phrasing that I used as well. They don't say it's an equivalence relation. They say it's a relation that, or something, it's an equivalence-like relation or something like that. Equivalence. Now, why the weird phrasing? Why not just say it's an equivalence relation if it has all the properties, transitivity, reflexivity, and symmetry? And the reason is not really that relevant because we're not doing things that formally when we construct this. Like I said, I will not define cardinal number for the same reason that I didn't define a natural number. And the reason is that it's very technical. It doesn't really belong in this course. And the naive or intuitive explanation is more than enough. If you're interested, I can provide some references for covering this in more detail. And I forgot to say this, but I did add some more references on Quercus. For every single topic that we've covered, I mentioned at least one or two textbooks that you can look at for additional exercises and to see how other people write about this. Okay, so I got a question in the chat. Is an equivalence relation connecting two elements of two sets? So an equivalence relation is always defined between, it's a relation on a set and itself, right? So yes, relations can connect different sets. For example, functions usually map from one set to a possibly different set, and relations do in general as well. But equivalence relation always are always defined on the same set. So this brings me to my next point. Why is this not really a relation? Why is this not properly defined? Why am I putting this in quotation marks, the word relation, and saying this weirdly, that it behaves like an equivalence? The reason is that relations are defined, like it was just pointed out to me in the chat. I think the private chat, so in case other people cannot see the question, I'm saying it out loud. Exactly. So Bill already got to the point. There is no set of all sets, right? And this relation is relating sets, pairs of sets. And the question whether two sets have the same size or not makes sense for any pair of sets. So this relation would have to be defined everywhere on all possible sets. And you might think that, well, that's kind of stupid. I mean, who cares that there's no set of all sets? But this is actually very problematic if we're trying to be very formal about this, because the axioms of set theory do not allow us to define a set of all sets, right? Now, we can prove that. We can prove that there is no set of all sets. Now, I cannot prove that to you now because we haven't really covered the axioms, so such a proof wouldn't make sense, right? For the same reason that you cannot prove very elementary things about the natural numbers before first answering, well, but how did you even define the addition of natural numbers? Or how do you even define this or that, if that makes sense? So for the purposes of understanding this chapter, you will just have to trust me that the best way to go about this is to do this informally, because it's not really a big deal. Unless you do set theory, no one really cares about this, and this is not a problem that will manifest itself in any other field that you're likely to encounter. So what's the point of me being this pedantic about things? Let me remind you what the construction is. What does it mean to be an equivalence relation, right? So if this is the universe, sorry, that's horrible. If this is the universe of all sets, let me call that universe. This doesn't exist, of course, but like I said, it doesn't really matter. Universe of all sets, right? The universe of all sets. Then this equivalence relation is cutting up this universe into pieces, as all equivalence relations do, right? Equivalence relations form partitions of whatever set they are defined on. For example, being congruent was cutting the integers into finitely many pieces that we called the modular classes, right? We've done examples of equivalence classes many times. That's how we constructed the integers, modular classes, the rationals, the reals. Everything is defined in terms of equivalence classes. So maybe I shouldn't repeat myself, but please let me know if this isn't clear. So for example, one set that we know that we're familiar with is the empty set. Now, the empty set is the only set that has no elements, because any other set with no elements has to be equal to that particular set, right? So that one is like a lonely set. This one is just in its own class, and there's no other set like it. Now, somewhere here, there's the set that contains a set containing just one element. For example, the set containing the empty set. This thing that I just wrote down, this thing right here, is a set with one element, but it's not the only one, right? For example, if I just add more brackets, more curly brackets, this is still a set with just one element. Namely, the only element it contains is the first set that I wrote down. So all of these have the same size, right? And every time you write a set with something inside and it's just one element, they all have the same size, and that size is 1, right? This is how we defined informally, like I said, the natural numbers. You're picking out one representative out of each class. Here's the class 0, here's the class of 1. What does the class of 2 look like? Well, it has to contain all the sets that have 2 elements. So for example, this is one element, the empty set. Now my second element cannot be the empty set again, because then I only have one element, right? It has to be different from the empty set. So well, we can just pick any set that is not empty, right? For example, this one. So that one is a set with 2 elements, right? The empty set and this other singleton. Now that's not the only set with just 2 elements. Of course, we can pick any set that contains A and B where A and B are different sets, right? All of these are congruent equivalent with this relation. So the whole class is what we call the number 2. We just pick one representative, right? So there's the class of number 3 and so on, right? Now, this is how we informally define the natural numbers, but of course, we can go on, right? There's some point in here where the natural numbers must make an appearance, right? So this set, what do we call the representative of that set? What do we call that amount, right? We need a name, a way to refer to the quantity that has the natural numbers. Now, if you're interested in knowing what we call that in set theory, this is called aleph naught or aleph zero. Aleph is the first letter of the Hebrew alphabet, if I'm not mistaken. Capitalized, maybe. Not really sure. So this is aleph naught, and that is the first infinite cardinal. But it is not the only infinite cardinal. As we will see in this chapter, there are sets that are strictly bigger than the natural numbers. Now, if this is the first time that you're listening to this fact, that you're hearing the fact that there are infinities of different sizes, then this might be very surprising. And it actually caused quite a bit of controversy when Cantor and other mathematicians came up with this theory, with set theory, right? And even though today it is perfectly well accepted and used by almost every field of math to, as foundations, there was a time where people actually rejected these ideas because they found them too weird. Maybe not this idea specifically, but some of the other ideas that you can derive from this. So the real numbers are not in bijection with the naturals. We will prove this. We will prove this, maybe not today, but as part of this chapter. So if you're interested what we call this cardinal, the name that is usually given is a C for continuum, right? So if you've ever encountered a textbook in analysis where it says there are continuum many continuous functions or continuum many points such that this function that, and that's what it is meant by that, right? It's an amount that is in bijection with the reals. Now, I'm very curious. Maybe you've taken this course before, so you know the answer to this question. But in case this is the first time that you're talking about this, can you give me an example of a set that is nowhere to be found right now? So an infinite set that I haven't covered yet in this huge infinite partition of the sets. Can you give me an example of a set that is bigger than the reals or bigger than the naturals or something like that? What other sets do you know that you've talked about in other courses? Okay, nice, nice. I'm getting a lot of answers. Complex numbers, integers, that's true. I mean, of course, right? We've talked about this. So let me spoil the theory a little bit. So the natural numbers, the integers, and the rationals are all in this class. There's a bijection between any two of these. So these all have the same size. This is surprising because it might seem like the integers, there's twice as many as naturals, right? Because the naturals just go to infinity on one side, but the integers go to minus infinity as well. So you might expect them to be more, but that's not the case. With the rationals, it's even worse because the rationals are dense. Between 0 and 1, there's already infinitely many rationals. So you might expect there to be much more rationals than there are natural numbers, right? The natural numbers are sparse, are discrete, are isolated, and yet the rationals are densely packed together. Why aren't there more rationals than there are natural numbers? This is something that maybe we even have time to cover today, why this is true. Sorry, some of you mentioned the complex numbers. So the real numbers are usually realized as a line, right? A number line, it's a linear order. The complex numbers are usually realized as a plane, and a plane contains infinitely many lines, continuum many lines. So you might expect there to be more complex numbers, but that is actually not the case either. There are no more complex numbers than there are real numbers. Any other sets? Any other sets? Have you taken linear algebra? Then you know many examples of sets and spaces with nice structures. So come on, give me one more example. Anything that comes to your mind, and we're going to put it here if it's easy enough. You can also try forming new sets with the sets we already have by using the operations on sets that we've talked about in this course. Union, multiplication, product, right? Functions or stuff like that. I'll give you one example that we can talk about. If you take the set of the collection of all subsets of the natural numbers, then this is also here. It is strictly bigger than the natural numbers, but it happens to be the same size as the reals. This isn't obvious, by the way. We're going to prove this at some point. Okay, I have another interesting example. I'm running out of space here, ironically. Okay, so another set that we can squeeze in here is if we take the real numbers and we remove the rationals, that is a set that has the same size as the real numbers. This is maybe not that surprising because we're removing a small set from a big set, even though both of them are infinite, right? Okay. Is there any other example that you can think of? Can you give me a bigger one? Something bigger. Okay, here's another idea. So Bill is saying if we remove the algebraic numbers, then yes, we would be in the same category as the reals. Yeah. Okay. I think we are going to mention algebraic numbers at some point, so maybe we can say R minus the algebraic. This is a lot more surprising if you know what algebraic means, right? Because algebraic numbers contain all the rationals, but they also contain a lot more. They contain pretty much every irrational number that you can name except e and pi. Okay. Can anyone give me a bigger example? I want something bigger because right now we only have two different types of infinity. By the way, you might be wondering, why did I call this aleph naught? Shouldn't there be an aleph 1? Shouldn't there be something that is slightly bigger? Because so cardinal numbers are going to be on a line, right? They are linearly ordered. So eventually there's aleph 0. The next cardinal number is aleph 1. I'm sorry, I cannot write these quickly for some reason. Aleph 1. Then there's an aleph 2. And this list goes on forever. Okay, power set of R, that's a good example. So the power set of R is actually bigger. So that has its own category. Okay, thank you, Ray. Now we have more examples. So one question that you can think about, and I'm happy to talk about that more if you want. Maybe this will spark your interest in set theory. So this is a list of cardinals, and it's not difficult at all to prove that this list must go on forever. There's no biggest cardinal number for the same reason that there's no set of all sets, but this is actually way simpler, and this is actually something that we can prove. Every time you have a set, we can find one that is strictly bigger, and Ray used that idea to produce this bigger set than R. Every time you take the power set of something, you're producing something bigger. Even for finite sets, right? The power set is always strictly bigger than the set you started with. This is already part of your problem set, by the way, but we are going to discuss it in the lectures at some point. So a natural question is, okay, this list goes on forever, but this list is a list of objects that are already counting things that go on forever, right? Most of these things, and by most I mean everything to the right of that line, is infinite. All of these cardinals are infinite, so they're counting things that are, they go on and on. So a question would be, what cardinality would this list have, right? What is the cardinality of cardinal numbers? So that's maybe I shouldn't write that down. Okay, so this is a naive approach. This is a naive approach. Naive is not a pejorative term. It simply means that I don't want to delve into the details of how we define these things formally, right? Because of course these objects do have a formal, very technical definition. I can tell you precisely what aleph 1 is in terms of sets. I'm not doing that now. And doing that would be maybe not a waste of time, but definitely out of the scope of this course. So this is a naive approach to cardinals. But it will serve our purposes. Now, hopefully this explanation will tell you why we use the following convention. This is just a convention if you're outside of set theory. If you're inside set theory, then this is not just a convention, it is actually the definition. So the convention is that if you have a natural number, which we didn't formally construct, but I just reminded you how we can informally do so, then n can be thought of as the set containing all naturals up to and including n minus 1, right? Now, why does this convention make sense? Well, like I said, the naturals and cardinals in general are just representatives of this huge relation. They're just picking out one particular example of a set with that amount of elements. So we might as well pick the easiest one. And the easiest one is, well, this, right? This set here contains n elements. So why don't we just call that the natural number n? So this is just a convention, and if you don't like it, you don't have to use it. Every time I use it in the problem set, I'm reminding you what this notation means in case it causes confusion. You don't have to use it, but I think it makes writing a lot of these theorems much easier. So what is the cardinality of the set that I just defined? Well, that is n, right? And this is true for all cardinal numbers. Every cardinal number is its own size because that's how we define it. This might seem abstract and nonsensical, but you're gonna have to trust me that this makes sense. And like I said, if you don't like this notation, you don't have to use it, right? It's not an essential part of the course. So this is just notation, if you will. But if you're curious, this is actually how the natural numbers are constructed formally, right? Maybe I should say the natural number 0 is, of course, representing the set that has no elements, right? That's how we expect this to work. So maybe this works for natural numbers bigger than 0. Anyway, okay. Do we have any questions so far? Great. Okay, so we can start talking about some actual proper definitions, right? Okay, okay, great. Right. So we defined this relation, and this relation is perfectly well defined, and it makes sense. So we should maybe start using it, right? We should start defining some things. Okay. Now I did post a quiz on Quirkus already. Give me a second. I just need to check what I put for a quiz. So there's clearly a distinction between cardinal numbers that are infinite and those that are finite. We have used the word finite before, even in the problem set. I think the first problem set uses the word finite, infinite in some sense. We haven't properly defined what that means. So here comes the first formal definition. A set A, well, let's call it X so that it's not that weird. A set X is finite if there is a natural number with the same size. So X is in bijection with the natural number n. So this means, if you don't like that notation, this means there is a function from the set, any set that has size n, but let's pick this one, and x, right? Not, that's, okay, bijection. Now this seemingly innocent definition already makes for some challenging facts. As you'll see, proving things in this abstract form is not as obvious as you might expect. So let's do a lemma. First lemma, just to start proving some things. So for any natural, there is no surjective function. I could write bijective, but we can prove that there's no surjective function. Actually, sorry, let's do it with injective. Injective function from n to a proper subset. Let's call it x again. Strictly smaller than n. Right? So if you have a natural number, then if you take a subset of a finite set, then the subset and the big set can never be in bijection with each other. This might seem obvious. I'm basically saying if you have a finite set and you remove stuff from it, then you make the set smaller, right? So removing stuff from a finite set makes it smaller. Now, this might seem obvious, but you'll see in a second the proof is far from obvious, and it is not true for infinite sets. Here we have several examples that we'll prove eventually. The simplest example I can think of right now is this one, right? Between the natural numbers and the integers, recall that we can think of the integers as a superset, or rather, the natural numbers are a subset of the integers. So we remove stuff to get the integers, the natural numbers. We removed half of it, right? All negative numbers. And yet the sets have the same size. So when we have an infinite set, it is true that we can remove an infinite amount of stuff from it, and the set hasn't changed the size. That is actually one way to define finite and one way to define infinite sets without having to construct the natural numbers. Because here, if you look at this definition at the top of the screen, I'm defining finiteness in terms of a pre-existing structure, which is the natural numbers. Now, shouldn't it be the case that you should be able to talk about whether something is finite or infinite without having to go through all this trouble? Do you know what I mean? Like, can you think of a definition of finiteness that simply talks about this relation that we defined? It doesn't need natural numbers to work or counting things to work. And the answer is yes. One way to define it, that is by using the lemma, right? This lemma is an if and only if, because you can always remove stuff from an infinite set without changing its size. In fact, you can always remove an infinite amount of stuff without changing its size. That's the first problem in your, or maybe second problem in your problem set, in case you're curious, or at least that's one way to interpret it in terms of into words. Okay, so does the statement of the lemma make sense? And hopefully I motivated a little bit why this lemma is important, even though it might seem like obvious, something obvious to prove. But this is actually not obvious at all. So any ideas? How would you prove this? And a hint that I give you is that this is a for any natural number statement, right? It's a statement that affects all natural numbers. So maybe you have a technique that will help. Okay, so Max suggests induction, and that's indeed what works. Someone else posted in the chat taking subsets. Yes, so we're going to do this by induction and then take a subset. Indeed. So the proof is induction on n. Right, so if n is 0, that's the basis case, then this is obviously true, right? This is vacuously true. You cannot find a proper subset of n because n is the empty set. There is no proper subsets of it. So there is no counterexample, right? The statement is saying for any natural number, there is no injective function from n to a proper subset. If that were false, then I would be able to find an injective function from n to a proper subset. So if my set has no proper subsets to begin with, well, of course, there's no hope of finding such an injective function. There's no counterexample to the statement. That is what I mean by vacuously true. We've talked about this in the very first chapter. So you can let me know if this is unclear. Okay, so induction and this is vacuously true. Now assume the statement for n, and we want to prove the statement for n plus 1, right? So how do we prove it for n plus 1? Well, we have to take a subset, as someone I think privately suggested in the chat. Okay, and take by contradiction, I think is the easiest way of writing this, an injective function. F, why not? From n plus 1, which is the number I'm trying to prove this for, to x, and x is, of course, a proper subset of n plus 1. Now recall, n plus 1 is a set, right? It's both a set and a natural number. It's the same thing. So if this notation doesn't make sense, then remember that we're treating n plus 1 as a natural number. And if you don't like that, well, then that is simply the set 0, 1, 2, 3, all the way to n, right? As I defined it earlier. Okay, so now we have to treat two cases in order to apply the hypothesis. So let me maybe sketch out what is happening. So this is the number 0, this is the number 1, this is the number 2, this is the number n, this is the number n plus 1. Do we need n minus 1? Right? And this is a function that is taking this whole thing and cramming it into a set x. Now, x is a subset, so it contains the same elements except for something that is missing, right? So for example, x could be skipping the number 1, then grabbing this one, then grabbing this one, something like that, right? Okay, that's the opposite of what I said. No, actually, it makes sense. So this could be the set x. It's picking out some elements, and it's missing at least one because it's a proper subset. And f is cramming everything on the left into the right. Of course, we know intuitively that's impossible because f is supposed to be injective. What happened here? Injective. Okay, I don't know what happened there. I think I was maybe saying function out loud and anyway. So that's what f is doing. This should be impossible, right? Of course, we cannot cram more elements into a smaller set. This is also known as the pigeonhole principle. But we will talk about that later in a different context. That is also part of chapter 6, which, like I said, they are intimately related. Okay, so we only have to divide into two cases and then derive the contradiction. Before I do that, I just realized it's already time for a short break. Let me pause this. Some of these very elementary proofs, as you might notice, are surprisingly challenging to figure out. I'll give you an example of this in a second. But before we do that, let's continue this. So what do we have to do? How are we going to derive a contradiction? Now, as you know, what we have to do is find an injective function from n to some subset of n, because that's how we will derive a contradiction. by induction, right? We have to reduce this to n. So how do we do that? How do we talk about just the first n elements? Well, you will notice that there's more than one possible case, right? So there's case 1, which I just wrote down. There's another possibility that's actually simpler to handle. So let's see if I can just copy this. Okay. So there's two possible cases, right? Either x contains this last element, n plus 1, or it doesn't. If it doesn't, then it's easy. Because if it doesn't, it means that all we have to worry about... okay. So maybe... How do I do this? Okay. That's not very nice. Sorry. How did I even do this? Whatever, right? Something like this. So this last element, n plus 1, may or may not be in x. If it is not, then this is very easy. Because if it's not in x, it means that f is cramming the first n natural numbers into x already. And x is a proper subset of n, not only n plus 1, but n, right? So case 2 is easy. Wait, cannot see. There you go. So case 2. Okay, let me change this so that makes more sense. Let's do the easy case first. Let's do the easy case first, right? So case 1, first possibility, n plus 1 may or may not be in x. So let's say that it is not in x. Then all we have to do is take the function f and restrict it to n, right? Because if we do this, then this function is still injective. It's a restriction of an injective function. But now it is sending that set to a proper subset of n, right? So does this case make sense? Actually, wait, I think I made a mistake. Sorry about this. Sorry, n plus 1 is not an element of n plus 1, right? It's only up to n. Sorry about that. So the biggest element in n plus 1 is n. You see, I got confused by my own weird notation, so apologies for that. It starts at 0 and it goes all the way to n. Okay. So either n, the last element, is an element of x or it is not, right? Okay. So since I got confused and betrayed by my own notation, maybe I should refrain from using it this much. Okay, you know what? Let's just change this and avoid this just for now until we all get used to it. So the notation simply means I am taking the first n natural numbers. There's n plus 1 of them. The first n plus 1 natural numbers, including 0. And I'm sending this to some proper subset. Let me just expand out this weird definition. Sorry, this weird notation to avoid confusion, right? That's all I'm doing. So on the left side, I have the first n natural numbers, or including 0, n plus 1, and I'm sending them to a proper subset, right? So either the last number n is in x or it is not. If it's not in x, then I don't have to worry about this because it means f is already sending the first n minus 1 elements into the set, right? So f restricted to n, and by n, of course, I mean the first n0 to n minus 1. And it is arriving at x, but x is not a subset. Sorry, x is a subset of this set because it doesn't contain n, right? Is still injective because it's a restriction of an injective function. So this function contradicts the inductive hypothesis, right? Look at the sketch. This function is taking this chunk of numbers and cramming them into x. And we already said that this is impossible because we are assuming that the statement is true for n. The statement being you cannot cram a subset. You cannot cram the first n natural numbers into a proper subset of it. But this is what f is doing, right? This is what f is doing if we ignore whatever happens to the number n because we don't care about n. So the one that's a bit trickier is the case number 2. What happens if n is in fact an element of x? This is more complicated because now how do we reduce this to something, right? We want a subset of 0, 1, 2, 3, all the way up to n minus 1. So somehow we need to shift the numbers. We need to shift what f is doing to get a contradiction. Okay. Let me see what's the best way of writing this? So for some k, let's say, in the domain, which is n, f of k is n, right? If n is in x, then it has to be, okay. You know what? It may actually be easier if I just assume this is bijective. It's going to be the same idea. No bijective function. Okay. Just, I don't want to divide in all these cases, and the lemma will be used for bijective functions anyway. Okay, I'm getting a question in the chat. Sorry, give me 1 second. Bijective. Okay, so the question in the chat is saying, shouldn't the proper subset of n not contain n minus 1? Proper subset of n. So n minus 1, there's no problem with n minus 1, right? Because this proper subset, this set has size n. So we're applying the hypothesis to that set of size n, right? And the hypothesis is saying there's no bijective function between n and a proper subset of it, right? Yeah, so it is still true that there's no injective function. I'm making the proof a little simpler so that we don't have to further divide into cases. Because now I have to say, well, if it's in the image, then we have to change this. Otherwise, we don't have to change this. But this is getting a bit too long. So let's just prove this for bijective function. It's the exact same thing, okay? Okay, so now there's some k that hits this number n because n is now an element of x, right? So there is some element k, maybe it's the number 2, that f sends to n, right? So now we have to shift it. We have to move it somewhere else. So how do we do that? This is where we use that it is a proper subset, which if you think about it, we haven't really used except for the inductive part. Okay, so how do we shift it? So now define g, and it's going to be a function from n, and by n, of course, I mean the first n indices, and it's going to be a subset of x, but I have to remove the last one, which is bothering me, f of k. Sorry, not f of k, that doesn't make sense. F of n. I want to remove that one, right? Because that one doesn't fit into the inductive hypothesis. The inductive hypothesis just talks about the set 0, 1, 2, 3, all the way to n minus 1. N cannot be a part of it. So now we define g, and g is basically going to shift is going to shift things around. So how do we define this? Let's see, how can we make sense of this? Okay, so I want G to cram this set that I'm circling in blue. Sorry, this set right here, I want it to be crammed into some proper subset of 0, 1, 2, 3, n minus 1. But there's a problem that it's sending k, in this case a number 2, to n. And I don't want that because then it doesn't fit into my inductive hypothesis, which only talks up to n minus 1, right? So I need to change it. I need to make a new function that sends that number 2 to some element that's not there. And if you think about it, I can pick anyone. Let me see. We can simply write this as, we can leave this unchanged when it's not the problem, right? When it's not causing any problems. Right? So for any I less than n that is not k, we know that f of I is not n. So we don't have to change those. We don't have to move those numbers. And where do you think we're going to send g of n? Where do we send it? We can simply send it to whatever f sends n to, right? Why does this make sense? Because f sends this element to what? Well, something that is definitely not n, right? Does this make sense? F doesn't send n to n because it's injective. It cannot send it to the same thing. So F must send n to something else, something that doesn't cause any conflict, something outside this problem. So the claim is that G is bijective. And this contradicts the inductive hypothesis. Why? Because G is a function from the set 0, 1, 2, 3 up to n minus 1 into a proper subset of it, which is x removing n. This is a proper subset, right? Now, this lemma I know might seem overly technical. Maybe it is. Maybe we can skip some of the other excessively technical things, but why is this lemma important? It seems so abstract, right? So here are some consequences of the lemma. So let's call this corollary. What is this lemma useful for? So the first consequence that we can reason is that if X is a set that has size n and X is a set that also has size m, then obviously these are the same natural number. Because if they weren't, well, then you could not find a bijection between them. But having bijections between them is transitive, right? So if both of them are in bijection with the same set X, they must be in bijection with each other. This is a fancy way of saying if there is a bijection between two natural numbers, between two sets that have the same size, then the sizes must be the same. Now, this is still, I agree, maybe a little technical because it might seem obvious, but it tells you that everything that we're doing about finite sets is well defined. This is well defined, right? Whenever you're proving something about bijections for a set, all you have to worry about is its size, and you can always swap it out, switch it out for some other finite set of the same size, and the same thing will be true. But the most important corollary of this is that n, the natural numbers, is not a finite set. Of course, we will call this an infinite set. Let's prove. I already said how to prove one out loud. It is simply a matter of applying transitivity and getting a contradiction from the lemma. But how do we prove two? How do you prove that the natural numbers are not a finite set, that they are not in bijection with the naturals? So this is the key part. Okay, so let's assume that the size of the natural numbers, as Ray says in the chat, were finite. Then it would need to have a largest number. Yes, yes, that is one way of proving it, right? So if it has a largest number, you just add one to it, and then you get something that is strictly larger. So that's a contradiction. But if you want to do this in a very formal way, using just the definition, using the fact, how do you get a contradiction from this, right? So suppose suppose um, that n has size for some natural number. So indeed, if this were the case, then you would be able to select the biggest number in the naturals, and then adding one to it would yield a contradiction, right? But this requires things that we haven't really proved. We can of course use them; it's fine. But we haven't really proved the fact that every finite set has a maximum element and stuff like that, right? So how would you do this just using the lemma? So there is a function from the naturals to 0, 1, all the way to n minus 1, right? The canonical example of the set of size n, which is that one, bijective. So why cannot this happen? I agree. I agree that if this were to happen, then n would be a list of n natural numbers. So the biggest one of them, which presumably would be n or something like that, you can just add one to it and get a contradiction. But that requires more knowledge that we haven't proved. If you truly think about this deeply, you will realize that even though that proof is very reasonable, and I agree, it's actually circular, right? How do you show that a finite set of natural numbers has a maximum element using the definition that I gave? If you really think about that, that's a circular argument because you first have to show that the natural numbers don't have this property. I mean, by circular, I don't mean that that's the only way of proving it. Of course, you could prove that separately, but that requires a similar thing that we just did, right? It requires an inductive proof where you take an element out of this finite set and say, is this the maximum? If it is, then we're done. If it's not, then you have to pick another one. And since you only have finitely many, eventually you're done. So you will have to have found the maximum element. So how do we derive a contradiction? The lemma says that natural numbers are never in bijection with each other unless they are the same, right? You can never take a natural number and squeeze it into something smaller. So in a way, this is telling you that the natural numbers can be squeezed into something smaller. So now take f, restrict it to the set, to itself, right? You restrict the set to itself. And what happens with this? Well, this will be in bijection. It's a restriction of an injective function, right? So it is still injective. And to make it bijective, well, you just take the image. So this is definitely a bijective function. And this is going to be a proper subset of the set. 0, 1. Why is it a proper subset? Well, because the f of n is not there. So in a way, it is using the same idea that Ray pointed out. But how do we prove that this exists? Well, if you really untangle this technical proof, this is actually proving that fact, just said in a different way. This contradicts the lemma. right? This might be too technical. This might be too technical, but I think it is good to know that if you really want to delve into the details, the formal details, then this is how you would have to do it, right? So where is Ray's idea? Sorry, I hope I'm crediting the right person. I've read many things in the chat. I think it was Ray. So regarding Ray's idea, where does that really come into play? So how is this the same thing? So this function, how would we prove that? I mean, this is obviously an injection and then a bijection when we take the image, right? So this is a bijective function. The thing is, how do we know this fact? How do we know that this is a proper subset? Because f of n is, sorry, f of n minus 1, I guess, in this case, is an element in the left that cannot possibly be on, sorry. F of n, I said it right the first time, is in here because everything is in there, right? Every natural number is in there. But it is not in here. F of n is not in here. So that's why this is a proper subset. It is missing f of n. And f of n is what Ray would call whatever number is bigger than the biggest number, right? So it is the same contradiction. It is the same idea that you're adding one to the biggest number to prove that the natural numbers cannot be finite. Now, sorry, I'm getting some more activity in the chat about the maximum element of the set. Can we take the additive inverse of all of them and form a new set? Okay, that's an interesting idea. So we take the maximum element and then the additive inverse of all of them and form a new set and then use the well ordering principle. Okay, I see. Right. So the idea is, what if we just take the additive inverse of all of these and then apply the well ordering principle? So this has a minimum, and the minimum is minus whatever is the maximum. So the reason that that wouldn't work is that if you take the additive inverse of a set, even if the set has is non-empty and is whatever bounded below, you cannot apply the well ordering principle because now you have a subset of the integers, right? So for example, if you take the set of all prime numbers, then the additive inverse is no longer has a minimum element. So I understand the idea, but the problem of proving that finite sets have a maximum element does not follow just from the well ordering principle. You need something stronger. You need something about finiteness, something like the lemma that we just proved now. Yes. But it is a good idea, and we could have proven this in some other way. Like I said, we can do a proof, a direct proof that every finite set of naturals has a maximum element. But if you really want to do that formally, you're going to need the lemma some way or another, or repeat the proof. It's also a proof by induction, right? So even though it might seem like this is overly complicated, I can assure you that if you want to do this very formally, you have to do something like this because the definition is just so abstract. It's just so abstract at first, right? Once we build some theory and have some theorems and definitions and stuff, we don't have to we don't have to do this anymore. We can just use the theorems. For example, we already proved something strong, that the natural numbers are not a finite set. Now, let me write down some other property. So theorem, something that you can think about is if A, B are finite, what kinds of operations preserve finiteness on these sets, right? So if you have two finite sets, then taking the union, sorry, is finite, right? So gluing finite sets together, if it's only finite amount of them, will still be a finite set. Moreover, and this is a symbol that we haven't defined in general, but of course it makes sense for finite sets because finite sets, we just have to add natural numbers, right? This inequality becomes equality when these are disjoint sets, right? If they are disjoint sets, if they share nothing in common, then taking the union is actually adding them together, right? But they could overlap, and if they overlap, taking the union might not necessarily make a much bigger set than adding them together, or the same size rather, right? So taking the union of finite sets preserves finiteness, and that is the first operation that we found. What about taking the intersection? This might seem obvious. So taking the intersection preserves finiteness for the reason that if A is a subset of B and B is finite, so A could, for example, be the intersection of B with something else, right? Then taking a subset of a finite set gives you a finite set. Now this was used somehow in the first problem set. I said you can just use it. Now, this theorem, the one I wrote above, will be proved formally in the tutorial. Proof tutorial. But this other theorem, I think we should just skip the proof because it is surprisingly more difficult. It is way more difficult than the lemma. Now, the reason it is difficult is not because this is very deep or anything. It's because the definition, when you go into the very core, into the very foundations of math, things become very abstract, right? It is difficult precisely because you cannot use anything. You cannot use the fact that finite sets have a maximum element because, well, we have to prove that first, and to prove it, we need this theory about finite sets in the first place, right? So I'm not even going to say this is an exercise. Let's just skip this one. And you can obviously freely use this easy intuitive fact that if you have a set, then any subset has to be finite as well, right? Skip because it's too technical. Now, what other thing can we say? Okay, so we have the union, we've covered the intersection. We can also cover the product. That one is not interesting because it is also covered in the tutorial and I just covered it at the top, right? So the product of finite sets is not only finite, but I told you how to calculate it, the size. And the size is n to the k, right? This doesn't just apply for the product, it applies for sets of functions even, of which I will define some notation in a second. But another operation that we've mentioned is the power set, right? So if x is finite, then the power set is still finite, even though it's bigger. So is power set. Now, proving this is part of today's quiz. So let me maybe draw an outline for you, and then you can fill in the details and upload that. So how do you prove this? How do you prove that if you have a finite set, then the collection of all the subsets is still a finite set? It might be a lot bigger, right? The power set, as the name suggests, grows exponentially in size. But here we don't care about the size specifically as a number, even though we could easily calculate it, and calculating this is also done in the tutorial. But how do you prove that it is finite in the first place? Using the definition or something like that. So what would you suggest? Any ideas? I can start you off with the first sentence, and then we will work through this together, and I think that's all we will have time for now. But yeah, it is the first section I wanted to cover. Why did this get deleted? Skip. Too technical. Too technical. Technical doesn't mean difficult. It doesn't mean hard. It doesn't mean deep. It just means that if we actually try to write this down, same with the lemma, it gets a bit excessive, and there's no need. There's no need for this, right? Okay, so the suggestion is induction on the size of of x. So first case, the base case, maybe let's write it using the kitchen recipe base case. If this is 0, then the power set of x is just the empty set, right? The only subset of the empty set is the empty set itself. So the power set contains only that, contains only the set itself. And this is obviously finite because it is in correspondence with the number 1. It is actually the number 1. If you think about this using the convention that I even managed to confuse myself with, this is the number 1, right? So it is obviously not just in bijection, it is the number already. This is the base case. Assume true for n, any set of size n, and take any set of size n plus 1. Right, so let's take x, and let's say it has elements x1, x2, dot, 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 xn. Okay, if I want to be consistent with my indexing, maybe I should start indexing with 0. So take any set of size n plus 1, which is the one I have right now. And how do we reduce the power set of x to something of size n? How do I use that information, the inductive hypothesis? You can split this into two things, right? So why don't we focus on the last fellow right here, right? So any subset of x either contains that last fellow or it doesn't. So if it doesn't contain it, well, then it's a subset of the set x with that xn removed. And if it does contain it, well, then this is just some set u. Okay, let me write this. U subset of x that contains xn. This is the only two possibilities, right? And these sets are obviously disjoint. Disjoint. Now notice that the set on the left, this one right here, has size n. Because I just removed an element from a set of size n plus 1, right? So by the inductive hypothesis, that power set is finite. The power set of x minus xn is finite. But what about this other set? What about this set right here? How do I show that that one is finite? I've almost given away the entire solution. You just have to use two facts. One of the theorems that I mentioned above, which tells you that the union of finite sets is finite, which will be covered in the tutorial, but of course you can assume that it is true now. And how do you convince yourselves that the blue set is finite? And by the way, are there any questions so far? We started off a bit maybe too formal. Not too formal, but the first lemma is too technical. But this is the only lemma that will be technical in this sense. The following ones will be a lot more. Following theorems will be a lot clearer, right? And we can always use this. So what do we do now? Can anyone tell me why the blue set is finite? Maybe we can make a sketch. Okay, we will not actually use. Okay, I'm getting some direct messages as well. Let me see. Okay, interesting. So we don't actually use the fact that x is finite. Wait, what happened? Something, for some reason, my chat glitched a little bit. I think I lost some of the, or did you remove them? Okay, so we won't actually use the fact that x is finite for this. We have to reduce that to the inductive hypothesis as well. Let me draw a sketch for you. We have 10 minutes to think about this together. And then if you have questions, I'm happy to give away the rest of the solution. But please make sure you try to write this up more or less nicely, or at least fill in the details that I skipped. Okay, so someone is saying that we can be more specific and say that the power set of x has size 2 to the n. Yes, that is correct. That is correct. But that is more specific than what we want here, right? That is even harder to prove. I mean, not a lot harder. It is a little harder to prove that what we're doing now. Right now, I only care about this being finite. If you want to prove that it is not just finite, but it has size precisely 2 to the n, then this is correct. But if we want to do that formally, we need to write a little bit more. We need to write a little bit more. We would be using something stronger to prove this result. So we can do that, but we have to prove that first, if that makes sense. So someone pointed in the chat, I think directly, that we cannot just say that p of x is finite. We can even say precisely what the size is, right? But for the purpose of this exercise, we don't require that. So what is the idea? The idea is that I have a set x and it has a bunch of elements x0, x1, x2. There's one particular element that I'm singling out, right? So every subset that lives here is in the power set of x minus xn. Every subset that does, however, contain this one element x is being counted separately. So how do you convince yourselves that that collection is still finite without using anything stronger, only using things that we've proved? Any ideas? What is the set? Okay, what is the size of that set, the blue set? Okay, so the union of two finite sets is finite. That is correct. That is how we conclude at the end. But to use that, we still have to show that these two sets that we're taking the union of are finite. So the first one, the one on the left, the one in red, this one, is finite by inductive hypothesis directly because it is the power set of a set of size n. But what about the blue one? How do you show that the set in blue is also finite? How many elements does it contain? Maybe I can draw a better picture for you, if that helps. If you don't figure it out, I should probably tell you the answer before the class is over, within the next minutes. Okay, so there's a new idea. By the inductive hypothesis, we take without xn is finite, and you okay. Yeah. Okay, so thank you, Ray and Max. Both of you have the correct idea. Exactly. So, okay. So this is this, right? This is the sketch of the set on the left, but how do we sketch the set on the right? So the set on the right, maybe let me copy this. So this is X. The set on the right consists of all subsets that do contain xn. So on the left, we're avoiding xn, but on the right, we have to contain it every time. So we take something and include xn. We take something and we include xn every time, right? We include something and we include xn. But if you think about it, whether we include xn or not doesn't change anything, because every time that we include xn, the rest of the set is something that, well, doesn't include xn, right? So these two sets, these two collections of sets have the same size. They just differ by some point, but that point is always fixed. So notice that the set on the left, which is the power set of xn the power set of x removing this is the same as the set in blue. If you want to write this down for the quiz properly, of course, you would give this set a name and not call it set in blue, right? This collection. Set in blue. Now why? You want to be very formal, which is the point of the exercise. We can just define a function, right? We can just define a function that goes set in blue if we want to be very formal. It goes to this other set and it grabs any element u, right? The set in blue contains elements that I called u, and they are all subsets of x containing the element x sub n. We can just send it and remove it if you want to be, if you don't like that notation, and remove xn from it, right? So what is this function f doing? This function f doing what is it doing? It's grabbing some set like this one, the one I'm highlighting in red right now, and it's removing the point xn. So what you're achieving is some set on the left. So this function is obviously bijective. If you don't believe me, then feel free to fill in the details, right? So this argument down here would prove that the set in blue is finite. And it is not just finite, but it is actually the same size as the one on the left. So following, I forget whose idea in the chat, the same argument can actually be used to show that px has size 2 to the n, because you split it into two pieces, and each piece has the same size. So it's doubling in size every time, and that's how you get 2 to the n. But to conclude that, you have to argue why these are disjoint, and argue something about the addition, and I didn't want to do that. So that's why I said, let's just prove that it is finite. It is a shorter argument. And if you want to have the correct answer to the quiz, then you should not use the fact that it has size 2 to the n, of course, because that's a stronger statement. And Yi Yang said, yeah, the total number of combinations is the same. That's exactly the reason, right? Oh, so it's as if you're adding a label to each set or adding something that all sets have, right? So it doesn't help you distinguish the sets if all of them contain xn. So you might as well remove xn from all of them, and then it's the same thing. Okay, I will stay here for a couple of minutes. Should you have any questions, let me stop the recording.